All right, gang, this next section, we're going to talk about type 1 improper integrals. Okay, there are actually two types, and we'll talk about type 2 improper integrals in a separate lecture. But just to give you an idea of what's going on here, let's just jump right in by way of an example. Consider the following. Okay, so here we have the function 1 over x squared, and it's defined on the interval 1 to infinity. Okay, so we're specifying what the domain is here. So a quick sketch of that graph. Bring that up. And what I'm going to do, gang, I'm just to illustrate the point and make the point, I'm going to exaggerate the graph a bit, okay? Okay, so that's what the graph looks like, just on the interval from 1 to infinity. What we would like to be able to do is calculate the area trapped beneath this graph over the horizontal axis from 1 to infinity. Now notice, if I highlight that, right, our intuition would suggest that because the graph never touches the x-axis, in other words, it doesn't have an x-intercept, that the amount of area that's trapped between the graph and the x-axis would be infinite. Okay, so it looks like the amount of area is infinite. Now, as in terms of an integral, actually, let me put it right here. In terms of an integral, gang, we would have this, right? Right, if we wanted to represent the area with a definite integral, it would have to look like this because the integral, or the graph is defined to infinity. Notice that the upper limit of integration is not a constant, okay? It's not a fixed number. We say that this is an integral defined on an open interval. That's what a type 1 improper integral is, okay? The other thing, gang, is why is it improper? If anything, the fundamental theorem of calculus tells us that in order to evaluate a definite integral, the function has to be defined on a closed interval, okay? So for the integral you're looking at right here, the fundamental theorem doesn't even apply. Don't go looking for an antiderivative for 1 over x squared because it's not going to help you in this case. There is, however, a clever workaround, okay? Consider this. Suppose somewhere after the 1, I locate a value for n, say here. Okay, so some number that's greater than 1, okay? Actually, you know what? Let's make it a specific point. Okay, can we calculate the area under the graph from 1 to 10? Can we do that? Yeah, actually we can, because the integral from 1 to 10 the fundamental theorem does apply. And so we know that the area from 1 to 10 is equal to 9/10. Okay, now that's a far cry from the total area. Remember, we're assuming that the entire area is infinite. Okay, well, the next thing I'm going to do is I'm going to take that number 10 and I'm actually going to push it out a little bit further, say maybe to here, and calculate all the area trapped up to the 20. I'll let you fill in the details, but if you do, Okay, you'll get that. Let's push out the 20 to the 40. Okay, now calculate all the area from 1 up to the 40. Okay, see what we're doing here, gang? What we're doing is we're trying to capture more and more area under the graph. Okay, so it's like we bite off a little bit more of the candy bar every time, right? We went to 1 to 10, 1 to 20, 1 to 40. Maybe we go 1 to 60. Let's go up to the 80. Okay, so and every time we push that red number out a little bit further to the right, we try to capture more and more area. Okay, now it won't fit on that graph up there, but if I go out to the 100, and remember again, all these separate integrals are defined on closed intervals, so the fundamental theorem applies. Okay, now notice notice what's going on here, okay? You know what we did? We generated, here, I'm gonna write the numbers like this. Okay, now we could keep going, right? We could very well keep going. What we've generated here is a sequence of numbers, okay? It's a sequence of numbers. Remember from our earlier days, like in pre-calculus, a sequence, simply put, gang, is just a list of numbers. But what do you notice about the numbers as we progress, as we read them from left to right? They're approaching 1. Yeah. So the amount of area that's underneath of this graph over here looks like it's not infinite at all. In fact, it looks like it's approaching a value of 1. Okay, it looks like it's approaching a value of 1. Okay, now let's do this. We could generate a sequence of numbers. We could use an Excel spreadsheet. We could use a calculator to do the same thing. I use a calculator to find these values here to make it go a little bit faster. But again, here's the idea. Okay, the value is, or the idea is, specify a generic value n, okay? And then take that value of n and continually push it out to the right, okay? Take off bigger and bigger chunks of area underneath of the graph, okay? Can we evaluate this integral the way that it is? No, the fundamental theorem does not apply. It's an improper integral. You don't have a closed interval. You have an infinite interval, okay? So a way to get around that is choose a value that's finite, some generic value, say capital N, or whatever letter of the alphabet you want to use, okay? And keep pushing that number out to the right over and over and over again. And what you're hoping is to generate a list of numbers like we did here, where you can see plainly that those values, so it's a limiting process, okay? It's a limiting process. And here we say that the limit approaches the number 1. Okay. Let's be a little bit more specific in this problem. Okay. All right, I'm going to sum up everything we did in the previous slide, okay? I'm going to take this integral and replace it with this one. Okay, now that value n is a finite number. And what we were doing in the previous, like right up here, we were taking that value of n and forcing it to get larger and larger and larger. The key point here, gang, is that on the inside of those square parentheses, you're talking about an integral that's defined on a finite interval, 1 to n. The fundamental theorem applies, and therefore we get the following. And notice now, when we take the limit of this expression, right, take the limit as n goes to infinity, notice that the first fraction goes to 0, and all that survives is the -1, which is equal to a +1, okay? So notice that the area that we were trying to capture is not infinite at all. Our intuition suggested it was so, but the mathematics shows that it isn't. We say, gang, when we have a type 1 integral like this, okay, a type 1 integral like this, and the result is a finite value at the end, we say that the integral converges to the number 1. So I'm going to make a note here. The improper integral 1 over x squared dx converges to 1. Okay, the improper integral converges to 1. Okay? Let's see for this one. Okay. Now this function, 1 over 2x plus 1 to the third, is certainly a positive function on the interval from 1 to infinity, right? So there is that at least. I lost my screen share. Okay, sorry about that, gang. All right, so this will actually, it'll represent area. The question is the area going to be finite or infinite? Okay, is this integral actually going to converge to something? We can't use the fundamental theorem. If you like, you can make a sketch. I think I'm just going to go right to it. Based on what we found above in the previous example, I'm going to rewrite this integral. And I'm going to replace the infinity symbol with a capital N, or whatever letter of the alphabet you like. Okay. Now, on the inside of the parentheses, we're talking about an interval defined on or integral defined on a closed interval from 1 to n. So now the fundamental theorem does apply. All right, so I'll use our techniques of integration that we learned previously. I see that I'm off by a factor of 2, so I'll fix that. All right, so I cleaned it up a little bit. Now I'm going to apply the limits. Okay, now we take the limit as n goes to infinity. And when we do, notice that the first fraction will go to 0, right? Because n is in the denominator and is growing without bound. And so all that's left will be the second term, which will wind up being positive 1. Oops, let's see. 2 plus 1 is 3 squared is 9. So that's going to be a 36, isn't it? And so therefore, we say that the original improper integral converges to the number 1 over 36, okay? Okay, so what about this one? Notice, gang, this is an improper integral. It's still a type 1, right? It's still a type 1, but notice that you've got an infinity symbol on the top and the bottom of the integral, okay? Now, when you have an improper type 1 integral like this, the idea is to pick a convenient value between negative infinity and positive infinity, to split the integral up into 2, right? Something convenient. A quick sketch of the graph of 1 over 1 plus x squared is this. Okay, 1 over 1 plus x squared. Quick sketch of the graph. So it looks to me, gang, that there's some symmetry there. I think what I'll do is I will choose x equals 0 for convenience, and I will split up my integral as follows. Okay, all right, so now here's what we have to do. In order to determine if the original integral, this one right here, converges, we have to first say something about these two separately. Okay, in order for the original first integral to converge, these two separate integrals have to converge themselves. It's possible that one might and the other won't. Okay, It's possible that the first one does, the second one doesn't, or whatever. Could be both of them don't. We won't know until we actually go through the process. If we don't get a finite value for either one of those integrals, all bets are off, gang. And we say that the original diverges. Okay, the original diverges. Okay, let's go figure it out. All right, let's do this. Let's do the first one right here. All right, so I'm going to replace this integral with this new one. Okay, so I replaced the negative infinity symbol with a capital N, or your choice, whatever letter of the alphabet you like. The fundamental theorem now applies on the inside of the parentheses, so apply it. Okay, now the first term, the inverse tangent of 0, right? The angle whose tangent is 0 is 0. But what about the second term? Okay, notice, gang, that the value for n is going to negative infinity. So think to yourself, what would be the angle, or the tangent rather, whose angle is infinite? Okay, what would that be? What do you think? Tangent of what angle would be negative infinity? Here, look. Here's a quick sketch in case you forgot. Okay, that's a quick sketch of the tangent function, right? That's the tangent. Okay, notice that the closer you get to negative pi over 2, the further down the graph goes to negative infinity. Okay, negative infinity. And so therefore, this second term is going to be negative pi over 2, or pi over 2. And so therefore, gang, the first integral up here, this one right here, we say that the first integral converges to the number pi over 2. So far, so good. Now we have to figure out this other one. Okay, let's see about it. You can probably guess this by the symmetry. Okay, now the second term, the inverse tangent of 0. So the angle whose tangent is 0 is 0. Okay, so this one right here, we got that one. Let's put it here. But the first one, what about this? What is the angle? Think to yourself, what is the angle whose tangent is positive infinity? Well, if you look up at the graph of the tangent function again, gang, notice that the closer you get to positive pi over 2, the higher the graph goes to, in other words, goes off the scale positive to positive infinity. And so therefore, the first one in the limit is equal to positive pi over 2. And so therefore, the second integral converges as well. All right, let's put it all together. So this tells us that the original improper integral is equal to the number pi, okay? So the improper integral converges to pi. If you go back up here, just to make sure we understand what it is that we found, okay? Remember, gang, this was the graph right here of 1 over 1 plus x squared. What we're saying is, even though the graph never touches the x-axis, and our intuition might suggest that the area therefore would be infinite, it's actually finite. The amount of area under that graph is equivalent to the value of pi, okay? So what is it about that, gang? Why does this not match our intuition? Well, think about it like this. Use a graphing calculator or Desmos and graph the function 1 over 1 plus x squared and blow up the picture continuously to the right. Okay, so in other words, shine the light on that part right there, if you will. And what you'll find, I'll put it down here. Okay, so it'll look like that. Look, and the further out to the right you go, gang, here's the area that's trapped between them. But notice when you zoom in, right, and keep going out to the right, there's going to be barely any daylight between the graph of the function and the horizontal axis. So what's happening? Is there area there? Yeah, there's area there, but it's so small, we say that it's negligible, and it adds no appreciable amount to the overall value of the area in question. So this is what we refer to as type 1 integrals. Okay, they're defined over infinite intervals, we say. Okay, and there was the first one that we did right there. In the next presentation, we'll look at improper integrals that are called type 2.